Greetings, chemistry students. Today we're going to finish up our notes on gases, heat, the kinetic molecular theory, all that good stuff. And I'm going to start with talking with you about a few terms that I want to make sure that you understand. You should be familiar with solids, liquids, and gases. Now, we can move from a solid to a liquid by adding heat, and we call that melting. We can move from a liquid to a gas by adding heat, and we call that either boiling or evaporation. But I'm going to combine those two terms into a term you may or may not know. We're going to call that vaporization. And the other thing you can do is you can move directly from a solid to a gas, and that process is called sublimation. This actually happens in your freezer when that's attached to your refrigerator. About once every day or two, it goes through a defrost cycle, and any frost that's in there undergoes sublimation, where it turns from a solid directly into a gas. You want to test this out for yourself, just take an ice cube and just set it on a shelf in your freezer, and you'll watch over the next couple weeks, it'll get smaller and smaller and smaller. Now, all of these processes involve adding heat, which is why I wrote them in red. We can do the opposite of these processes by removing heat, also known as cooling them down. We can go from a liquid to a solid, and as you all know, we call that freezing. We can go from a gas to a liquid. We call that condensation. That's what that water that forms on the outside of a cold beverage when it's sitting out at room temperature. If you take a drink out of the refrigerator and you get that water on the outside, that's condensation. It's water vapor in the air, turns into a liquid as it releases heat when it comes into contact with the container. And we can go from a gas directly to a solid. This process is called deposition. This is how frost forms in the wintertime. Water vapor encounters a very cold surface and it immediately turns into ice. Frost is not dew that then freezes. That's a different thing and much more difficult to deal with. So I just want to make sure you're familiar with what these terms are before we delve into today's actual lesson. Concepts, we've got this thing called the heat of fusion. And fusion is not talking about nuclear fusion where you're taking two atoms and putting them together. This term is much older than that. It essentially means fusion is an old-fashioned way of saying to melt. For instance, if you fuse two things together, you can do so by melting them, pushing them together, and waiting until they solidify. Also, a device called a fuse that's used in electrical circuits. If things get too hot, it melts and interrupts the flow of electricity. But heat of fusion is the amount of heat that's needed to melt 1 gram of a substance, or it's the amount of heat that is released by freezing 1 gram of a substance. And the amount of heat that's needed to melt or to freeze is the same. It just depends on if you're adding heat, it melts. If you're releasing heat, it freezes. There's a simple formula that's on page 3 of your reference tables that says Q equals M times HF. It's found right there on page 3 of your reference tables. And HF is the heat of fusion constant. And with this formula, the other thing to know is that when you're melting, the potential energy of the particles that you're working with increases. In other words, when you're melting something, the particles move farther away from each other, kind of like how there's gravitational potential energy you probably learned about in middle school, where the energy increases as you raise an object up off the ground. Well, for when we're talking about molecules, their potential energy increases as they move farther apart from each other. I'm going to go on and show you the next slide, and then I'll work through a couple of examples for you. So the next slide is heat of vaporization, which is the amount of heat needed to vaporize 1 gram of a substance, or the amount of heat released by condensing 1 gram of a substance. So vaporization is for the transition between liquid and gas. Q equals m times the heat of vaporization constant, where HV is the heat of vaporization constant. And when you're boiling or vaporizing, the potential energy of the particles increases, and when you're condensing, it decreases. So those are our 2 formulas for the day. Now we're going to go back and we're going to look at a few examples. So I could ask you a problem like, how much energy is required to melt 10 grams of ice? Well, the equation for melting, that's heat of fusion, so our mass is 10 grams. Let me make that look more like a 10. That almost looks like a 16. So 10 grams of ice times the heat of fusion constant, which if you look on the front of your reference tables, it tells you the heat of fusion of water is 334 joules per gram. So you multiply those together and you get 3,340 joules. In a similar vein, I could ask how much energy is released when 10 grams of steam condenses. Well, condensation, that's condensation and vaporization are 2 sides of the same coin. So we're going to be using the heat of vaporization. So Q equals M times HV. So 10 grams times, now I look on the front of our reference tables, the heat of vaporization for water is 2,260 joules per gram. So you multiply that together and you get 22,600 joules. But one last thing I want to show you today is something called a heating curve. I'm going to take and sketch out a little graph for you where we're going to have heat, which is represented by the letter Q. We're going to have temperature, represented by the letter T. Now, if we take a substance, such as water, for example, and we start at, let's say this is in kelvins. We start at 0, where at absolute 0, there's no heat. As we start adding heat, the temperature will rise because it's solid and we're heating it up until we get to a very specific point, which would be 273 kelvins, also known as 0 degrees Celsius. At that point, that ice would stop increasing in temperature and it would begin to melt. And that happens at exactly the melting/freezing point. And the temperature will stay constant while it melts because instead of making the particles move faster, you're actually causing the particles to separate from each other. So that's what the difference is with melting. Then, once you've melted all that ice, you've now got water. The temperature can keep going up until it reaches 373 kelvins, or 100 degrees Celsius, or 212 Fahrenheit, at which point it will begin to boil, and the temperature will remain constant again until all of the water has boiled away and turned into a gas. If you were to capture that gas and keep applying heat, then the temperature could continue going up again. So at this point along the curve, we're going to use Q equals M times H V, and down here, Q equals M times H F. So here we've got solid, liquid, gas. If we're going from left to right, this would be melt. If we're going from left to right, this would be vaporization. If we were going the opposite way, that would be condensation. And here, if we go from left to right, that would be melting. The other thing to point out is that if you wanted to calculate how much heat is involved down here with the solid or the liquid or the gas, as its temperature is changing, you would use Q equals MC delta T, the specific heat formula we learned about yesterday. So keep in mind on your reference tables, you've got heat of fusion for water, that's for the solid liquid transition. You have the heat of vaporization for the liquid vapor transition. And then you actually have three different specific heat constants depending on whether you're talking about a solid, a liquid, or a gas. So the actual value of the specific heat constant C changes depending on what point in this curve you're on.